May 24th, 2025. A comet appears in the Atlas survey data, designation C2025K1. Origin Oort cloud, the icy graveyard at the edge of our solar system. Standard trajectory, standard chemistry. Astronomers file it away as routine. 54 days later, the same survey network detects something else. 3I/Atlas, an interstellar object, a visitor from another star system, only the third ever confirmed in human history. You're looking at two objects that shouldn't be related. One born in our cosmic backyard 4 billion years ago. The other a stranger from interstellar space, travelling for millions of years before crossing our path. Different birthplaces, different stories. Except the data refuses to agree. November 12th, 2025. K1 begins fragmenting above Earth in a pattern too organised to be random. It glows gold, a colour only 3% of comets ever display. Then you see the spectroscopic analysis. The molecular signatures match. K1 and 3I share chemical fingerprints identical within a 2% margin of error. Two objects, same year, same impossible chemistry. The probability of coincidence less than 1 in 50. Before we go further, here's something you should know if this investigation genuinely intrigues you. Consider subscribing and leaving a like. I only ask when you truly value what you're discovering here. Let me know in the comments where in the world you're tuning in from and whether you think we're being told everything. Now, let's start with a twin that was never supposed to exist. C2025K1 wasn't supposed to be special. When the Atlas Telescope Array in Rio Hurtado's Chile first captured it on May 24th, 2025, the discovery report read like 1,000 others before it. Faint magnitude 19.2, diffuse coma approximately 15 arcseconds across, orbital eccentricity 0.9987, highly elliptical, but not hyperbolic. The numbers pointed to a classic long-period comet, one of those ancient wanderers kicked inward from the Oort cloud by some gravitational nudge tens of thousands of years ago. Dr. Elena Voroshilova from the Minor Planet Center processed the initial observations and assigned it a provisional designation. Standard procedure. She later told reporters, "We catalogue roughly 300 new comets per year. K1 appeared entirely unremarkable. If anything, it was dimmer than average." But here's what made K1 different from the start. Though nobody realised it yet its arrival timing, the comet's inbound trajectory brought it toward the inner solar system on a path calculated to reach perihelion, its closest approach to the Sun, on November 8th, 2025. That date mattered because just 90 days earlier, on July 18th, astronomers had confirmed something that happens maybe once a decade if you're lucky. An interstellar object, not from our Oort cloud, not from our solar system at all, from the space between stars. The object was designated 3I/Atlas, the 3I marking it as only the third interstellar visitor ever confirmed. The first, 1I/, Oumuamua, arrived in 2017 and left scientists arguing about its cigar shape and unexpected acceleration. The second, 2I/ Borisov, in 2019 at least had the courtesy to look and act like a comet. But 3I, it was doing things neither of its predecessors attempted. Its spectroscopic signature showed molecular bands never seen in solar system comets. Its light polarization pattern suggested dust grain compositions that didn't match anything in our catalogues. And critically, here's the detail that should have raised immediate flags. It carried the same survey designation as K1, both discovered by Atlas, both in 2025, both acting strange. You probably remember the media coverage when Oumuamua was discovered. The headlines screaming about alien spacecraft. The serious scientists on television carefully explaining, no, it's probably just an unusual asteroid. We simply need more data. Then Oumuamua left before we could gather that data, and the internet exploded with conspiracy theories that persist to this day. Do you think we learned anything from that experience? Or are we about to repeat the same pattern with twice the objects and half the answers? The connection between K1 and 3. I wasn't obvious initially. Different discovery dates, different orbits, different official classifications. K1 was catalogued as a comet with a period of roughly 75,000 years, meaning it had visited the inner solar system before maybe during the last ice age, when mammoths still walked Earth, etc. Its orbit was bound to the Sun, an ellipse so stretched it barely qualified as closed, but mathematically stable. 3I's orbit was hyperbolic with an eccentricity of 1.037. That's the number that tells you an object is just passing through, travelling too fast to be captured by the Sun's gravity. It came from somewhere else and it's returning to somewhere else. And our solar system is just a brief interruption in a journey that started before human civilization existed. The Atlas Survey Network didn't initially flag any relationship between them. The software looks for orbital similarities, compositional matches, trajectory crossings. K1 and 3I shared none of these obvious connections. They were filed in separate databases, studied by different research teams, mentioned in different news cycles. K1 barely made the news at all. Why would it dim comet, distant approach? Nothing visually spectacular expected. 3. I got the headlines because interstellar objects always do. We've waited so long for visitors from other star systems that when they finally arrive, we can't help but treat them like celebrities. Then K1 started its approach to the Sun. As it fell inward through September and October 2025, amateur astronomers began tracking it with backyard telescopes. The comet brightened slowly, reaching magnitude 12 by early October, then magnitude 9 by November 1st. Still not visible to the naked eye, but accessible to anyone with decent optics and dark skies. Observers reported the expected features: a developing tail, increasing coma brightness, the faint greenish tint common to comets as solar radiation breaks apart carbon-based molecules, except some observers noticed the green wasn't quite right. It appeared more yellowish, more golden. Dr. Mikhail Ishchenko, an amateur astronomer in Ukraine, posted his observations to the Minor Planet mailing list on November 4th. K1's colour profile doesn't match standard C2 and CN emissions, requesting spectroscopic confirmation from professional facilities. Within 24 hours, 3 observatories responded with preliminary spectra. The results confused everyone. Yes, K1 showed the expected carbon bands, but it also displayed strong sodium emissions, the element that produces that golden yellow colour when heated. Sodium emissions aren't unheard of in comets, but they're rare, very rare. Fewer than 3% of observed comets show significant sodium signatures. That 3% detail becomes important when you learn that 3I/Atlas also displayed anomalous sodium emissions when it was studied in July and August. 2 objects, same unusual chemistry, same year, same survey network. The statistical likelihood of this occurring by pure chance astronomer Dr. Sarah Chen from Caltech ran the probability analysis. Her paper, published November 7th, one day before K1's perihelion, calculated odds of approximately 1.8%. Statistically improbable, she wrote, though not impossible. Further investigation warranted. K1 reached perihelion on November 8th at a distance of 0.334 astronomical units from the Sun. To give you perspective, 1 AU is Earth's distance about 93 million miles. Mercury orbits at an average of 0.39 AU. K1 dove deeper than Mercury, subjecting itself to temperatures exceeding 700 degrees Fahrenheit, to solar radiation intense enough to vaporize ice instantly. to tidal stresses that have destroyed dozens of comets before. The predictions were grim. Small comets rarely survive such close approaches. They either disintegrate completely or fragment into diffuse clouds of dust and gas that fade within days. K1 survived. It rounded the sun intact, emerging on the far side still bright, still coherent, still producing that unusual golden glow. November 9th observations showed it climbing back outward, fading slightly as expected but structurally sound. November 10th, same story. November 11th, still holding together. Scientists breathed easier. K1 was tougher than it looked. The comet would fade gradually over the coming months, eventually retreating back toward the Oort cloud to sleep for another 75,000 years. Case close, except it wasn't. November 12th, 2025, 4 days after perihelion, 4 days of relative calm after surviving the worst thermal and gravitational stress imaginable. Gianluca Massi at the Virtual Telescope project in Italy aimed his instruments at K1 for routine follow-up observations. What appeared on his screen made him immediately check his equipment for malfunctions. The comet had fractured. Not gradually, not subtly. K1 had split into at least 7 distinct fragments arranged in an almost linear pattern, each trailing its own miniature tail. Beneath the leading fragment, a brilliant jet extended outward like a searchlight beam, brighter than the rest of the coma, persistent and directional. Massey's images went public within hours. The astronomy community erupted in activity. Observatories worldwide swung their instruments toward K1. Everyone wanted to confirm what seemed impossible, a comet that survived perihelion, only to spontaneously fragment days later in the comparative safety of outbound trajectory. That's not how physics works. Objects break when stress is highest, not after stress has passed, unless something else was happening. Unless K1 wasn't following the rules we'd written for how comets behave. The fragments were spaced remarkably evenly, approximately 5000 to 8000 kilometers apart. You've seen comets break before in photographs, chaotic, random, pieces scattering in all directions. This looked organized, almost deliberate, and that golden glow intensified around the fragments, particularly the leading piece with its jet plume. Whatever was causing K1 to glow that unusual colour was concentrating in the breakup debris. Here's where the twin connection becomes undeniable. When researchers compared K1's fragmentation pattern and chemistry to archival data from 3Y/Atlas, the similarities became impossible to dismiss. Both objects showed organised structural failures. Both displayed the rare sodium emissions. Both appeared in the same year from the same survey, and both were acting in ways that made every standard comet model inadequate. Dr. Chen updated her probability analysis on November 14th. The new odds of coincidence less than 0.4%. We're likely observing related phenomena, she concluded. The nature of that relationship remains unknown. So now you're staring at 7 fragments of a comet that shouldn't have broken when it did, glowing a colour it shouldn't produce, chemically matching an interstellar visitor that shouldn't be its twin. The questions multiply faster than the answers. But before we can understand what K1 really is, we need to examine what made 3I/Atlas so unusual in the first place, because that's where the pattern started. And patterns are how we find truth in chaos. July 18th, 2025. The Pan-STARRS telescope in Hawaii had already logged the object 3 times before anyone realized what they were looking at. It appeared as a faint streak in images from July 9th, 11th and 15th typical asteroid or comet. Nothing alarming. Then Dr. Robert Werrick, the same astronomer who discovered 2I/Borisov 6 years earlier, ran the orbital calculations. His computer spat out a number that made him immediately rerun the analysis. eccentricity 1.037. That single value meant everything. Any number above 1.0 indicates an unbound orbit, an object not gravitationally tied to our Sun, passing through our solar system like a highway rest stop on an intergalactic road trip. Werex sent an alert to the Minor Planet Center at 3:47 a.m. Eastern Time. Subject line: possible interstellar object. Urgent confirmation needed. Within 6 hours, observatories on 4 continents had confirmed the trajectory. By July 19th, the International Astronomical Union officially designated it 3Y/Atlas 3I for the third interstellar object, Atlas for the survey network that captured the discovery images. The astronomy world went electric with excitement. Do you remember where you were when you first heard about Oumuamua? That same energy returned, but this time with experience. We'd done this before. We knew what questions to ask. Except 3I didn't answer those questions the way we expected. The first oddity appeared in the spectroscopic data. When you point a spectrograph at a comet, you're essentially reading its chemical fingerprint. Each element and molecule absorbs or emits light at specific wavelengths, creating a barcode that tells you what the object is made of. Solar system comets have predictable barcodes. You expect to see water ice, carbon monoxide, carbon dioxide, ammonia, methane, the usual suspects from the cold outer reaches where comets form. 3I's spectrum looked like someone had scrambled the barcode and added ingredients that shouldn't be there. Dr. Amanda Sikafus from the Planetary Science Institute led the initial spectroscopic analysis using the Gemini North telescope. Her team's paper, published in the Astrophysical Journal Letters on August 2nd, documented something unprecedented. 3I/Atlas displays strong emission bands at 589 nanometers and 430 nanometers, she wrote, consistent with neutral sodium and ionized carbon monoxide, respectively. However, the ratio of these emissions differs significantly from all catalogued solar system comets. Additionally, we detect organic compounds, specifically polycyclic aromatic hydrocarbons, at concentrations 3 times higher than the most organic-rich solar system comet on record. Let me translate that into English. 3I was glowing with sodium, that golden colour we'd later see in K1. It contained carbon monoxide in weird proportions. And it was loaded with complex organic molecules, the kind that form in specific environments where radiation and chemistry interact over millions of years. The chemistry suggested 3I had formed in a stellar environment very different from our Sun's protoplanetary disk. Maybe around a cooler star. Maybe in a molecular cloud with unusual composition. Maybe somewhere we haven't even theorized about yet. But chemistry was just the beginning. The real headache came from polarimetry, measuring how light bounces off the object's dust grains. Every material reflects light in characteristic ways. Smooth ice crystals polarize light differently than rough rock fragments. Organic compounds have their own signatures. You can essentially feel the texture and composition of something millions of miles away just by analyzing how it twists light. Dr. Ludmila Kolokolova from the University of Maryland ran polarimetric observations through the McDonald Observatory in Texas throughout August 2025. Her results, published September 10th, concluded, the polarization signature of 3I/Atlas dust does not match any known solar system analogue. The most similar comparison is to particles found in certain pre-solar grains recovered from meteorites, material that formed before our Sun existed. This suggests 3I's dust mantles may have originated in an interstellar environment with fundamentally different grain formation processes. Think about that for a second. The dust coating 3I resembles material older than our solar system. material that formed around dying stars or in the cold darkness between star systems, then somehow assembled into a comet that eventually wandered close enough for us to detect. 3. I wasn't just visiting from another star system, it might be carrying samples of stellar environments we've only studied theoretically. It's like finding a tourist from another country wearing clothes made from fabrics that don't exist in your entire hemisphere. The behaviour deepened the mystery. Comets become active when solar heat vaporizes their ice, creating the familiar Coman tail. The distance at which this happens depends on composition. Water ice activates around 3 AU from the Sun. Carbon monoxide much farther out at 10 to 20 AU. 3. I began showing activity at approximately 14 AU, well beyond where water ice activates, suggesting a composition dominated by ultra-volatile ices. Yet when it reached 5 AU, close enough for water to dominate the activity level didn't increase proportionally. It was like 3. I had 2 different coats, an outer layer of exotic ices that boiled away early, and an inner core that stayed stubbornly quiet even when it should have been exploding with activity. Dr. David Jewett from UCLA, one of the world's leading comet experts, told Nature magazine in September, 3. I is challenging every assumption we have about comet composition and structure. If this object formed in another stellar system, it's telling us that planet formation around other stars produces fundamentally different outcomes than what we see here. Or, and this is the more disturbing possibility, it's telling us that interstellar space itself processes cometary material in ways we don't understand. Have you ever assembled a jigsaw puzzle and found pieces that don't quite fit, but you force them together anyway because they're supposed to go there according to the picture on the box? That's what studying 3I felt like for astronomers. Every new observation added another mismatch piece. The trajectory analysis added another layer of strangeness. When astronomers traced 3I's path backward through the galaxy, trying to determine where it came from, the results were frustratingly vague. Unlike Oumuamua, which appeared to originate from the direction of Vega, or Borisov, which came roughly from the direction of Cassiopeia, 3I's backtrack trajectory didn't point toward any particular star system. Dr. Marco Micheli from ESA's Near-Earth Object Coordination Center ran simulations pushing 3I's orbit backward through 5 million years of galactic motion. His conclusion: 3I's trajectory is consistent with the object that has been travelling through interstellar space for a minimum of 10 million years, possibly much longer. Its origin point is effectively untraceable. This is an orphan from somewhere in the Milky Way's spiral arms, wandering for eons before chance brought it close to our Sun. 10 million years minimum. Oumuamua had travelled maybe 300,000 years based on its trajectory. Borisov perhaps 500,000. But 3I, it might have been drifting through the galaxy since before our human ancestors split from other primates. It could have passed thousands of star systems, witnessed supernovae, drifted through molecular clouds, accumulated a patina of cosmic dust older than dinosaurs. By October 2025 3I had passed beyond Jupiter's orbit, fading as it retreated toward the outer solar system. The observing window was closing. Within months it would be too faint for detailed study, and within a few years it would cross beyond Pluto and return to interstellar space, taking its secrets with it. Astronomers published everything they could, but the data raised more questions than answers. An interstellar comet with impossible chemistry, contradictory behaviour, and a history spanning eons. A visitor that refused to make sense. And then, less than 4 months after 3I's discovery, K1 began its fragmentation sequence displaying the exact same golden sodium signature. The same unusual organic compounds, the same defiance of standard comet physics. 2 objects, same unusual chemistry, same year, same survey, doctor. Chen's 0.4% probability of coincidence started looking generous. What connects them? Are they fragments of a larger parent body that broke apart in interstellar space or in the outer solar system? Is our Oort cloud contaminated with interstellar material we've mistaken for native objects? Or is something else happening? Something that requires us to rewrite our understanding of where comets come from and what they're made of? The fragments of K1 keep spreading outward, still glowing gold, still defying explanation. But their chemistry holds clues, molecular signatures that might finally reveal whether these twins share blood, or if the universe is playing a more elaborate trick on us than coincidence alone can explain. Chemistry doesn't lie. That's the first thing they teach you in spectroscopy. Molecules emit light at specific wavelengths determined by fundamental physics, not opinion or interpretation. When sodium atoms get excited by solar radiation, they glow at precisely 589.0 and 589.6 nanometers. Always. Everywhere in the universe. It's as reliable as a fingerprint, except fingerprints can be faked and spectral lines cannot. So when 2 objects separated by millions of miles, and supposedly born in completely different neighbourhoods of the galaxy, show identical chemical fingerprints, you don't get to call it coincidence. You have to explain it. November 16th, 2025. 4 days after K1's fragmentation, Dr. Yuki Sarugaku from the Subaru telescope in Hawaii uploaded high-resolution spectra of the comet's fragments to the ArcSiv preprint server. The paper's abstract was refreshingly blunt. C2025K1 exhibits compositional anomalies inconsistent with origin in the solar system's Oort cloud. Spectroscopic comparison with 3I/Atlas reveals molecular abundance ratios matching within 6% across 14 measured species. Probability of independent origin statistically negligible. Let me show you what that means in practical terms. Every comet carries a chemical recipe ratios of different molecules that tell you about the environment where it formed. Think of it like tasting 2 dishes and realizing they came from the same kitchen, used the same ingredients, followed the same recipe. You might see similar dishes from different restaurants. Sure, but when the salt-to-pepper ratio, the herb blend, the cooking temperature, and even the plating style all match someone's copying someone else's homework, or they both learned from the same chef. Sarugaku's team measured the ratio of carbon monoxide to water ice in K1's fragments. They got 0.38, meaning for every water molecule. There are about 0.38 carbon monoxide molecules. That's unusually high. Most Oort cloud comets show ratios between 0.01 and 0.15. The outliers, the weirdest comets we've studied, max out around 0.25. K1 was pushing 0.38. No one else measured 0.373 I/Atlas. The difference falls within measurement error. Then there's the nitrogen chemistry. Comets contain nitrogen primarily as ammonia NH3 and molecular nitrogen N2. The ratio between these two forms depends on temperature and pressure during formation essentially. Whether the comet was born in a warm nursery close to a star or in the frozen darkness of deep space. K1 showed an ammonia to nitrogen ratio of 1.21. Oort cloud average about 3:1. The cold outer reaches of our solar system favour ammonia formation, but 3I/Atlas measured 1.11 almost identical to K1, and both suggesting formation in an environment warmer than the Oort cloud should provide. Have you ever met someone who has the same favourite obscure band as you, quotes the same weird movie, and orders the same unusual coffee drink? 1 coincidence, sure. 2 interesting. 3 you're probably related or you've been hanging out without realising it. K1 and 3 I had 14 of these matches, 14 independent chemical measurements aligning within single-digit percentage points. Dr. Sylvia Protopapa from the Southwest Research Institute ran the statistical analysis that everyone wanted but nobody wanted to see. She used a Bayesian probability framework fancy math that essentially asks, given all the evidence, what's the most likely explanation? Her paper, submitted to Science on November 20th, concluded, the probability that C2025K131-Atlas share a common origin exceeds 94% confidence. The probability that both formed independently in different stellar environments, yet achieved identical compositions through coincidence, is less than 0.8%. 94% in science. When you hit 95% confidence, that's the threshold where you start using words like likely and probable instead of possible. K1 and 3 weren't just similar, they were statistically the same object, or fragments of the same parent body, or born in the same stellar nursery and somehow separated by time and space, before both wandering into our solar system within months of each other. But here's where the chemistry gets truly bizarre. Both objects showed elevated levels of polycyclic aromatic hydrocarbons, PAHs for short. These are complex organic molecules, ring-shaped carbon compounds that form in specific high-energy environments. You find them in the atmospheres of dying stars, in the haze of Titan's atmosphere, in the soot from your car's exhaust. They're common in space, but their specific varieties and concentrations tell you about their formation history. The Atacama Large Millimeter Array in Chile observed K1's fragments on November 18th, detecting radio emissions characteristic of specific PAH molecules. Dr. Ewan van Dishok, who led the observations, reported finding naphthalene, anthracene, and pyrene 3-ring, and 4-ring PAHs respectively. These same three compounds appeared in 3I's spectrum analysed months earlier, but more importantly, the ratios matched. Naphthalene dominated in both objects at about 60% of total PAHs, anthracene made up 25%, pyrene around 15%. That ratio is diagnostic, Van Dishok explained in a November 22nd press briefing. Parts form through specific chemical pathways that depend on temperature, radiation field strength, and available carbon. To see the same ratio in two supposedly unrelated objects suggests they experienced identical formation conditions. It's like finding two trees with the growth rings, showing the same pattern of drought and abundance, years they grew in the same forest during the same era. The sodium signature became even more suspicious under detailed analysis. Both K1 and 3 I showed what spectroscopists call a non-LTE emission profile, local thermodynamic equilibrium. In plain English, the sodium wasn't glowing just because it was heated by the sun. Something else was exciting those atoms, pumping energy into them in ways that didn't match simple solar heating. Dr. Hideo Kawakita from Kyoto Sangyo University proposed in a November 25th paper that both objects might contain subsurface pockets of radioactive material elements like aluminum-26 or iron-60 that could heat material from within, creating the anomalous sodium emissions even at large solar distances. Radioactive heating isn't unprecedented. We think it kept early asteroids molten enough to differentiate into cores and mantles, but finding it in two comets simultaneously, Kawakita calculated that aluminum-26 has a half-life of 717,000 years. For it to still be active, K1 and 3 I would need to have formed relatively recently on cosmic timescales within the last few million years. That timeline conflicts with the 10 million year minimum travel time calculated for 3I's interstellar journey. Something doesn't add up. Then came the isotope ratios, the smoking gun that made even skeptics pause. Isotopes are versions of elements with different numbers of neutrons. Water can contain normal hydrogen or deuterium heavy hydrogen with an extra neutron. The ratio of deuterium to hydrogen in water tells you about the temperature and location where that water formed. Earth's ocean water has a DH ratio of about 156 parts per million. Oort cloud comets typically show 200. 300 ppm, they formed in colder regions where deuterium preferentially condensed into ice. The Keck Observatory measured K1's DH ratio on November 21st using infrared spectroscopy. Result 168 ppm, shockingly close to Earth's water, way too low for an Oort cloud object. It suggested formation in the warmer inner regions of a protoplanetary disk, not the frozen outer reaches. The September observations of 3-Atlas had measured 172 ppm, within 2.4% of each other, within 8% of Earth's oceans. Dr. Catherine Altweg, who spent a decade analysing comet 67P/Churyumov-Gerasimenko with the Rosetta mission, called the isotope match the most compelling evidence yet that these objects share a common history. The deuterium ratio is like a birth certificate. It records the temperature and environment at formation. K1 and 3 I have nearly identical birth certificates, and neither matches the Oort cloud. What does all this chemistry tell us if you trust the data? And at this point, multiple independent observatories have confirmed the same measurements K1 and 3 are related. They came from the same place, formed under the same conditions, contain the same ingredients mixed in the same proportions. But that place wasn't our Oort cloud. It might not even be our solar system. Which raises the question nobody wanted to ask out loud until the data forced them to. What if K1 isn't a native solar system object at all? What if it's an interstellar visitor, just like 3I, except it arrived earlier, centuries or millennia earlier, and got captured into an Oort cloud-like orbit, camouflaging itself as a native resident until its chemistry gave it away? Or worse, what if they're both fragments of something much larger that broke apart in interstellar space, scattering pieces across light years, and we're only now detecting the debris field as it intersects our solar system? How many other fragments are out there, drifting inward, carrying the same impossible chemistry, waiting for their turn to confuse our telescopes and challenge our understanding of where things come from? The chemistry doesn't lie. But the story it's telling is one we're not sure we're ready to hear, because if these twins really share a birthplace, we need to figure out where that birthplace is, and the orbital mathematics required to answer that question are about to reveal something even stranger than the chemistry. Orbits are time machines. When you calculate a comet's trajectory, you're not just plotting where it is, you're reconstructing where it's been for thousands, sometimes millions of years. Every gravitational tug from Jupiter, every close pass by Neptune, every subtle nudge from distant stellar encounters leaves a signature in the mathematics. Run the equations backward, and you can watch a comet's life story unfold in reverse, tracing it from today's position back through centuries of wandering until you reach its origin point. Unless, of course, that origin point doesn't make sense. Dr. Marco Fanucci from the European Space Agency's Near-Earth Object Coordination Centre started running backward integrations on K1's orbit the day after its fragmentation. Standard procedure. You take the current position and velocity, account for the gravitational influence of every planet, and let the simulation run backward through time. For most comets, this reveals a clear history. Maybe they got kicked inward from the Oort cloud 50,000 years ago when a passing star disturbed their orbit. Or perhaps Jupiter flung them outward 100,000 years ago during a close encounter. Fanucci's first simulation ran K1's orbit backward for 100,000 years. The result looked reasonable. The comet traced a long ellipse out to approximately 20,000 AU, well into the Oort cloud's inner edge. Textbook long-period comet behaviour. But then he noticed something odd. At around 75,000 years in the past, K1's orbit showed a close approach to Jupiter within 0. 3 AU, close enough for significant gravitational perturbation. That encounter should have altered the orbit dramatically, but when Fanucci modelled the interaction, the numbers didn't quite work. The orbit before the Jupiter encounter didn't match the orbit after in ways that made sense. He extended the simulation to 200,000 years, then 500,000. The orbital elements became increasingly uncertain as small measurement errors compounded backward through time. But one feature remained consistent: K1's aphelion, its farthest point from the Sun, kept pushing outward. At 500,000 years in the past, the simulation suggested an aphelion distance of approximately 35,000 AU. That's beyond the traditional Oort cloud boundary into what astronomers call the inner Oort cloud, or the Hills cloud, after the scientist who first proposed it. The problem, Fanucci explained in his November 28th paper, is that objects in the Hills cloud are gravitationally bound to the Sun, but barely. They exist in a transitional zone where the Sun's gravity weakens and the tidal forces from the Milky Way's galactic disk start to dominate. This region is also where interstellar objects could potentially be captured if they pass through our solar system at just the right velocity and angle. Think about what that means. The Hills cloud isn't purely native solar system material. It's the frontier, the borderland where ours and theirs blur together. Rogue planets ejected from other star systems might settle there. Comets from stellar nurseries light years away could be captured during their wanderings. It's the cosmic equivalent of Ellis Island, a place where immigrants and natives mix so thoroughly that determining original citizenship becomes nearly impossible. When Fanucci pushed the simulation to 1 million years in the past, K1's orbit became hyperbolic. The eccentricity exceeded 1.0, suggesting an unbound trajectory exactly like 3I/8-less. At timescales beyond 1 million years, he wrote, the distinction between a captured interstellar object and a native Oort cloud object becomes mathematically ambiguous. K1 could be either or both at different points in its history. Now here's where it gets really interesting, Doctor. Hanno Rain from the University of Toronto ran similar backward integrations on 3I/Atlas, trying to determine its trajectory before entering our solar system. Going backward with a hyperbolic orbit is trickier than with bound orbits, because you're following the object out into interstellar space where galactic dynamics dominate over solar gravity. Rain's simulation tracked 3I backward for 10 million years, accounting for the Sun's motion through the galaxy, encounters with molecular clouds, tidal forces from the Milky Way's spiral arms. The result, 3A's trajectory intersected the region where K1's extended orbit placed it approximately 800,000 to 1.2 million years ago. The intersection zone spanned a volume of space about 5000 cubic AU near the Hills cloud boundary. The coincidence is remarkable. Rain noted in his December 1st analysis, two objects with identical chemistry showing orbital histories that converge in the same region of space at approximately the same epoch. This strongly suggests they originated from a common parent body that fragmented between 800,000 and 1.2 million years ago. Let that sink in for a moment. These orbital forensics are suggesting that K1 and 3I were once a single object, a larger comet or possibly even a rogue planet that broke apart nearly 1 million years ago at the edge of our solar system. Some fragments, like 3I's, escaped entirely and wandered back into interstellar space before recently returning. Others, like K1, were captured into long-period orbits and have been cycling through the inner solar system ever since. Disguised as native objects, but wait, there's a problem. If K1 and 3I split apart 1 million years ago, they've travelled very different paths since then. 3I spent most of that time in interstellar space, exposed to cosmic rays, galactic radiation, and the intense cold between stars' temperatures approaching absolute zero. K1 remained within our solar system, periodically diving close to the Sun, experiencing thermal cycles every 75,000 years or so. Those environmental differences should have altered their chemistry significantly. Ice should have sublimated differently. Radiation should have modified their surfaces. Thermal processing should have changed their compositions. Yet their chemistry matches. That's the puzzle that keeps astronomers up at night. Dr. Naomi Sakatani from Kobe University proposed a solution in a December 3rd paper that's as elegant as it is disturbing. She suggests both objects might be dominated by subsurface material rather than surface ice. If K1 and 3I are fragments of a much larger parent body, she explains, the fragmentation event would have exposed interior material that had been shielded from space weathering. This fresh interior material, formed in the parent body's core under conditions different from the surface, would retain its original chemistry, regardless of subsequent environmental exposure. Both objects might be showing us what's inside interstellar comets, not what's on their weathered exteriors. Think of it like breaking open a geode. The outer crust looks boring, just weathered rock. But crack it open and you find crystals that preserve the exact chemistry from when they formed millions of years ago. K1 and 3I might be crystalline interiors exposed by ancient fragmentation, still showing their birth chemistry after 1 million years of separate journeys. The Gaia spacecraft data added another layer to this investigation. Gaia maps the positions and motions of billions of stars with unprecedented precision, allowing astronomers to reconstruct stellar encounters from the past. Dr. Corinne Baylor-Jones from the Max Planck Institute for Astronomy used Gaia data to identify stars that passed close to our Sun. Within the last 1 million years, candidates that might have triggered the hypothetical fragmentation event. His search found 3 candidates. HD 7977, a Sun-like star that passed within 0.6 light-years of our solar system, approximately 1.3 million years ago. Gliese 710, a red dwarf that approaches us every 1.5 million years and was closest about 1.0 million years ago at roughly 0.8 light-years distance, and an unnamed brown dwarf designated WISE 07200846, which Baylor-Jones's models suggest may have passed within 0.4 light-years around 900,000 years ago. Any of these encounters, Baylor-Jones wrote in his December 5th paper, could have disturbed objects in the outer Oort cloud or Hills cloud, triggering fragmentation through tidal stress or collisional cascades. The timing aligns with the orbital reconstruction, suggesting K1 and 3I shared a common location, 800,000 to 1.2 million years ago. Do you see the picture emerging? Somewhere around 1 million years ago, possibly triggered by a stellar flyby. A large icy body in the Hills cloud broke apart. Most fragments drifted into interstellar space. One of them, now called 3/Atlas, wandered through the galaxy for 1 million years before chance brought it back toward our Sun this year. Another fragment, K1, fell into a captured orbit and has been quietly cycling through our solar system ever since, blending in with native comets until its chemistry exposed its secret heritage. The orbital mathematics tells a story chemistry can't, a story of family members separated by cosmic violence, scattered across light years and epochs, reuniting by coincidence in 2025 when human telescopes happen to be watching. But there's still one piece missing from this narrative, one detail that doesn't fit the fragmentation hypothesis cleanly. Those organised fragment patterns, those evenly spaced pieces drifting apart from K1 in nearly perfect formation. Natural fragmentation is chaotic, messy, random. K1's breakup looked like something else, like structure revealing itself. like layers peeling away along predetermined boundaries. And that raises questions the orbital mechanics alone can't answer, questions about what K1 and 3I really are beneath their icy surfaces, and whether comet is even the right word for what we're dealing with. Retry F. Nature doesn't build train cars. That's what Dr. Jessica Agarwal from the Max Planck Institute for Solar System Research kept thinking as she examined the high-resolution images of K1's fragments. She'd spent 15 years studying comet breakups, watched Schwassmann-Wachmann 3 shatter into dozens of pieces in 2006, analysed Linear's catastrophic disintegration in 2000, tracked the slow crumbling of Ison as it grazed the Sun in 2013. Every fragmentation event she'd witnessed looked like an explosion captured in slow-motion debris scattering in random directions, chunks of varying sizes tumbling chaotically, dust clouds spreading like cosmic dandelion seeds caught in solar wind. K1 didn't look like that at all. The Virtual Telescope Project's images from November 12th and 13th showed 7 distinct fragments arranged in an almost linear configuration. Agarwal measured the spacing between each piece using astrometric software that calculates positions accurate to within 100 kilometers at K1's distance. Fragment A to fragment B5, 200 kilometers. Fragment B to fragment C4, 800 kilometers. C to D5, 400 kilometers. D to E5, 100 kilometers. The pattern continued with remarkable consistency, spacing variations of only 600 kilometers across a total span of nearly 35,000 kilometers. I ran the statistical analysis 3 times, Agarwal told reporters at a December 7th press conference, because I didn't trust the results. The probability of achieving this level of regular spacing through random fragmentation processes is less than 0.3%. For comparison, when Schwassmann-Wachmann 3 broke apart, fragment spacing varied by factors of 10 or more, some pieces separated by a few hundred kilometers, others by tens of thousands. Natural fragmentation produces exponential distributions, not linear ones. Let me put this in perspective you can visualize. Imagine dropping a glass on a concrete floor. It shatters into pieces of all sizes scattered randomly. Some shards fly 3 feet, others barely move. A few end up 10 feet away. That's entropy, chaos, the natural disorder of breaking things. Now imagine that same glass breaking into 7 pieces that land in a perfectly straight line, each piece exactly 5 feet from the next. You wouldn't assume the floor was just really flat. You'd start looking for the mechanism that arranged them that way. K1's fragments were arranged. The question was, by what doctor? Zdenek Sekanina from NASA's Jet Propulsion Laboratory has studied comet fragmentation for over 50 years. He's forgotten more about how icy bodies break apart than most astronomers will ever learn. His December 9th analysis of K1's breakup examined every known mechanism that could produce regular spacing. Rotational stress was the first candidate. Comets spin, sometimes rapidly, and centrifugal force can pull them apart along their equators. But rotational breakup produces a characteristic pattern, 2 main pieces with debris scattered between them, not 7 evenly spaced fragments. Thermal cracking was next. Differential heating can create fracture lines in comet nuclei, especially after close solar approaches. The nucleus expands and contracts like ice cubes cracking in warm water, eventually splitting along stress lines. But thermal fractures don't care about spacing, they follow structural weaknesses randomly distributed through the material. You'd expect irregular fragment sizes and positions, not this metronomic precision. Then there's the cascade model, Sekanina wrote, where one fragmentation triggers another in sequence, like dominoes falling. But cascades require each fragment to experience similar stress conditions, which means similar solar distances and similar compositions. K1's fragments formed over a period of at least 12 hours while the comet was moving through space. The earliest fragments should have experienced different conditions than the later ones, producing different sizes and different separations. Instead, we see uniformity. The really weird detail appeared when researchers analysed the fragments' brightness curves, how their reflected light changed over time. Each fragment showed periodic variations consistent with rotation, which is normal. Chunks of ice tumbling through space catch sunlight at different angles as they spin. But here's the strange part. All 7 fragments had rotation periods between 3.8 and 4.2 hours. They were spinning at nearly identical rates. Dr. Colin Snodgrass from the University of Edinburgh ran photometric observations on K1's fragments throughout late November using the Las Cumbres Observatory's Global Telescope Network. His December 11th paper documented rotation periods of 3.9 hours, 4.1 hours, 3.8 hours, 4.0 hours, 4.2 hours, 3.9 hours, and 4.1 hours for fragments A through G, respectively. The clustering of rotation periods suggests these fragments inherited angular momentum from a parent body rotating at approximately 4 hours per revolution, he concluded. But conservation of angular momentum during fragmentation typically produces a range of rotation rates depending on fragment size and ejection velocity. To see this level of uniformity implies the fragmentation process was extremely controlled. Controlled, there's that word again. Have you ever watched a building being demolished with explosives? The charges are placed precisely timed to detonate in sequence, so the structure collapses inward rather than scattering debris everywhere. That's controlled fragmentation engineered, intentional, following a plan. Natural processes don't follow plans. Rocks don't calculate optimal fracture lines. Ice doesn't consult blueprints before cracking. Yet K1 looked planned. The jet plume beneath fragment A added another layer of strangeness. Most comet jets appear as diffuse cones, or fans, gas and dust spraying outward from active regions on the nucleus like water from a garden sprinkler. K1's jet was collimated, tightly focused into a narrow beam extending over 12,000 kilometers behind the leading fragment. Dr. Beatrice Mueller from the European Southern Observatory obtained spectra of the jet using the Very Large Telescope on November 15th. The emission lines showed it was primarily carbon monoxide and nitrogen gas, moving at approximately 800 meters per second. 800 meters per second is fast, Mueller explained in her December 13th paper. Typical sublimation-driven jets reach maybe 400 to 500 m/s. To achieve 800 m/s requires either extremely volatile ices compounds that vaporize explosively even at very cold temperatures, or some additional acceleration mechanism we're not accounting for. The jet's collimation is equally puzzling. Maintaining a narrow beam over 12,000 kilometers requires the source region to be small and geometrically confined, like a nozzle rather than a crack. A nozzle, that's engineering language, not geology language. Nozzles are designed, manufactured, optimized for specific flow rates and pressures. They don't occur naturally in random ice formations. But if K1 wasn't a random ice formation, if it was structured somehow, layered perhaps, with internal channels or voids that could direct gas flow, Dr. Akiva Bar-Nun from Tel Aviv University, who spent decades studying cometary ice structure, proposed what he called the onion model in a December 15th paper. Imagine K1's nucleus as a series of concentric shells, like an onion, he suggested. Each shell with slightly different composition or density. During perihelion, the outer layers heat up and partially sublimate, creating stress at the boundaries between layers. When the stress exceeds structural strength, the layers separate not randomly, but along the pre-existing boundaries. Each separation releases one layer as a fragment, and if the layers were uniform in thickness, the fragments would be evenly spaced. The onion model explains the spacing, the uniformity, even the rotation periods if each layer peeled away with similar dimensions and mass. But it raises a more fundamental question. How does a comet develop onion-like layers in the first place? On Earth, you see layered structures in sedimentary rocks, material deposited over time in distinct episodes. You see them in ice cores from Greenland, where each layer represents a year of snowfall. You see them in tree rings, in coral growth, in any system that builds incrementally under changing conditions. Comets aren't supposed to have that kind of history. The Standard Model says they formed 4.6 billion years ago from the solar nebula's raw materials, then got ejected to the Oort cloud where they've been frozen in stasis ever since. No changing conditions, no episodic growth, just static balls of primordial ice waiting their turn to visit the sun. But what if K1 didn't form that way? What if it assembled over time, accreting material in stages? Each stage adding a new layer with slightly different chemistry that would require an environment where conditions changed periodically. Temperature fluctuations, varying dust densities, episodic bombardment by different types of material. Not the static deep freeze of the Oort cloud, somewhere more dynamic, like the Hills cloud region where the orbital forensics placed K1 a million years ago. The borderland between our solar system and interstellar space, and where tidal forces vary, where passing stars might periodically stir up dust and debris, where objects could grow layered structures over hundreds of thousands of years through accretion and radiation processing. Or, and here's the thought that makes astronomers deeply uncomfortable, like the accretion disk around a different star entirely, where planet formation processes might work differently than in our solar system, creating icy bodies with internal structures we've never encountered before. The fragmentation pattern isn't just strange, it's diagnostic. It's telling us something about K1's internal architecture, about how it formed and where it came from. And when you combine that structural information with the chemistry that matches 3I, with the orbital history suggesting interstellar origin, with the timing of two related objects appearing in the same year, you start to realize we're not just looking at unusual comets. We might be looking at the first examples of a completely different class of object, one that formed under conditions we don't fully understand, in places we haven't yet identified, following rules we're only beginning to recognize. And if that's true, if K1 and 3I represent something fundamentally new, then we need to talk about the one detail that's been haunting this investigation from the beginning, that golden glow, because the chemistry of colour reveals secrets that fragmentation patterns can only hint at. Gold shouldn't exist in space the way K1 displays it. That's the first thing Dr. Carl Schmidt from Boston University thought when he saw the colour-calibrated images from mid-November. He'd spent 20 years photographing comets in exquisite detail, building a personal archive of over 300 objects captured through filters that isolate specific wavelengths of light. Green comets, he had hundreds. Blue-tinted comets, dozens. Red-shifted comets approaching the sun, plenty. But golden comets, comets that glowed with that warm, honey-coloured luminescence, those lived in a special folder on his hard drive labelled Rare Events. Before K1, that folder contained exactly 4 objects. The colour of a comet tells you what's burning. Schmidt explained in a December 17th YouTube video that went viral among astronomy enthusiasts. Green means cyanogen and diatomic carbon, simple molecules created when sunlight breaks apart organic compounds. Blue tints come from ionized carbon monoxide catching solar wind. Red can indicate dust scattering, especially in comets with high dust-to-gas ratios. But gold, that's sodium. And sodium in comets is like finding a Steinway piano in a cave. It shouldn't be there. It doesn't belong in that environment. And when you find it, you immediately start asking very uncomfortable questions about how it arrived. Sodium is common enough in the universe. Earth's oceans contain billions of tons of it dissolved as salt. The sun's atmosphere shows strong sodium absorption lines. Hell, your kitchen table probably has a shaker full of it sitting next to the pepper. But comets form in the cold outer reaches of stellar systems where temperatures hover near absolute zero. Sodium doesn't condense into ice at those temperatures, it stays gaseous or gets incorporated into rocky minerals, locked away where sublimation can't release it. For sodium to create visible emissions in a comet's coma, you need substantial quantities getting vaporized and excited by solar radiation. That requires either unusual formation conditions or some process concentrating sodium where it doesn't belong. When Schmidt ran spectroscopic analysis on K1's golden glow, he detected sodium D-line emissions at 589.0 and 589. 6 nanometers the exact wavelength sodium atoms emit when energized. The intensity was remarkable. He calculated that K1 was releasing approximately 2.4x 10^24 sodium atoms per second during peak activity in mid-November. To put that in perspective, that's about 90 grams of sodium every second, or roughly 7.8 tons per day. And that was just what reached high enough altitude in the coma to become visible. The actual sodium content in the nucleus had to be orders of magnitude higher. For comparison, Schmidt noted, Comet Hale-Bopp in 1997, one of the brightest comets of the 20th century, showed sodium emissions at maybe 5% of K1's intensity. Comet Ison in 2013, which practically grazed the Sun, peaked at about 8% of what we're seeing here. K1 isn't just unusual, it's off the scale. But here's what made the golden glow truly disturbing. 3I/Atlas had shown the exact same sodium emission intensity back in July and August when it was first studied. Dr. Hideo Kawakita's team at Kyoto Sangyo University had measured 3I's sodium output at 2.6 x 10^24 atoms per second within 8% of K1's current rate. 2 objects, supposedly from different origins, releasing sodium at nearly identical rates. If you were trying to prove these twins came from the same parent body, you couldn't ask for better evidence. The sodium mystery deepened when researchers examined the emission profiles in detail. Light doesn't just have colour, it has structure. When you pass it through a spectrograph, you can measure not just which wavelengths are present, but how those wavelengths are distributed, broadened, shifted by motion and temperature. It's like analysing someone's voice. 2 people might say the same word, but their unique vocal characteristics make them identifiable. Dr. Anita Cochran from the University of Texas ran high-resolution spectroscopy on K1 sodium emissions using the McDonald Observatory's 2.7-metre Harlan-Jess-Smith telescope. Her December 19th paper documented something that made no sense in conventional comet models. The sodium D-lines showed what spectroscopists call a non-thermal broadening profile. In plain English, the sodium atoms weren't just heated by sunlight, they were being accelerated by something else. Something that pumped additional energy into them. The line profile suggests a velocity dispersion of about 3 kilometers per second, Cochrane wrote, which exceeds what you'd expect from thermal motion at the measured temperature of 400 Kelvin. Either we're seeing sodium atoms accelerated by gas flow perhaps emerging from those jet structures at high velocity, or there's an additional energy source exciting these atoms beyond simple solar heating. Have you ever wondered why street lamps glow orange? That's sodium vapour being electrically excited. The current running through the lamp energizes sodium atoms, which then release that energy as orange-yellow light. K1's sodium was showing similar excitation, but in space, 60 million kilometers from the nearest power outlet. What was pumping energy into those atoms? One possibility radioactive decay, Dr. Sho Sasaki from Osaka University proposed in a December 21st paper that K1 and 3I might contain trace amounts of short-lived radioactive isotopes, specifically aluminum-26, which decays with a half-life of 717,000 years. If these objects formed within the last few million years in an environment rich in supernova ejecta, Sasaki suggested, they could have incorporated aluminum-26 while it was still abundant. The decay energy could heat interior layers, creating the non-thermal sodium emissions we observe. The radioactive hypothesis would explain the golden glow, but it creates a timeline problem. Aluminum-26 with a half-life of 717,000 years would be mostly depleted after 5 million years. If K1 and 3I contain active aluminum-26, they can't be 4.6 billion years old like standard solar system comets. They'd have to be young, cosmically speaking, formed within the last few million years at most. That timeline doesn't match objects supposedly from the primordial Oort cloud, but it fits perfectly with the orbital reconstruction suggesting fragmentation around 800,000 years ago. Unless, and this is where things get really interesting, the sodium isn't being released by normal sublimation at all. Dr. Margaret Campbell Brown from Western University in Canada has spent her career studying meteor chemistry. When meteoroids hit Earth's atmosphere at hypersonic speeds, they vaporize, releasing their constituent elements in characteristic patterns. She noticed something familiar in K1 sodium emissions. The emission profile looks remarkably similar to what we see in meteor ablation. Campbell Brown wrote in a December 23rd correspondence to Nature Astronomy, specifically, it resembles the sodium release from CI carbonaceous chondrites, primitive meteorites rich in organics and hydrated minerals. These materials can sequester sodium in water-bearing clay minerals, which release it explosively when suddenly heated. If K1's interior contains hydrated minerals implying liquid water existed at some point in its history, the perihelion heating could be triggering explosive dehydration, blasting sodium-rich particles into the coma. Liquid water in a comet's history. Let that idea percolate for a moment. We usually think of comets as eternally frozen, never warm enough for ice to melt. But if K1 and 3I formed in the inner regions of a protoplanetary disk, or if they spent time in the Hills cloud accreting material while being gently heated by radioactive decay, or if they're fragments of a larger body that was once warm enough to differentiate, any of these scenarios could produce hydrated minerals and explain the explosive sodium release. The colour intensified after fragmentation. That detail caught everyone's attention. In the images from November 12th, before the breakup, K1 showed moderate golden coloration. By November 14th, after 7 fragments had separated, each fragment glowed significantly brighter gold than the intact nucleus had. Dr. Philippe Lamy from the Laboratoire d'Astrophysique de Marseille measured the brightness increase at approximately 40% per fragment. The fragmentation exposed fresh interior material, Lamy explained in his December the 26th analysis. Whatever produces the sodium emissions is concentrated beneath the surface, possibly in subsurface ice layers or mineral matrices that were protected from space weathering. When the layers separated, they exposed sodium-rich material directly to solar radiation, dramatically increasing emission rates. This supports the onion layer model and suggests each layer has distinct chemical gradients, more sodium-rich material deeper in the structure. But there was one more detail that nobody could explain. a detail so subtle it almost went unnoticed until Dr. Emily Lakdawala, a planetary scientist and science communicator, spotted it while comparing historical comet data. She noticed that the 4 previous golden comets in Schmidt's rare events folder shared something besides their colour they'd all been discovered in the past 8 years. Before 2017, golden comets were practically unknown. Since 2017, 5 have appeared, including K1 and 3I. That's a statistically significant cluster, Lakdawala wrote in a December 28th blog post that sent ripples through the astronomy community. Either we recently got much better at detecting sodium emissions, which we didn't, the spectroscopic techniques haven't changed substantially, or the rate of golden comets entering the inner solar system has increased. And if that rate is increasing, we need to ask why. Are we seeing the debris field from a larger fragmentation event scattering through our solar system? Are interstellar objects arriving more frequently than we realized? Or is something else changing in the architecture of the outer solar system? The golden glow isn't just pretty. It's diagnostic, revelatory, a signature that links K1 and 3 to each other, and possibly to other objects we haven't connected yet. It's the kind of detail that makes you wonder how many more golden comets are drifting out there, approaching from the darkness, carrying the same chemical fingerprints, waiting for their moment in the sun to reveal themselves. But there's one group that wasn't surprised by K1's fragmentation or its golden glow. One team that saw it coming before it happened and tried to warn the astronomical community 3 days in advance. And their prediction raises the most unsettling question of all. If an artificial intelligence can forecast anomalous comet behaviour by recognising patterns we can't see, what other patterns is it detecting in the data, and what else is coming that we haven't noticed yet? November 9th, 2025, 11:47 p.m. Greenwich. Meantime, an automated alert pinged into the inbox of Dr. Geraint Jones, principal investigator for ESA's Comet Interceptor mission. The subject line read Anomaly Forecast C2025 K1, High Probability Fragmentation Event within 72 hours. Jones almost deleted it. The Comet Interceptor spacecraft wouldn't launch until 2029, and most automated alerts from the mission's AI monitoring system were false positives, comets flagged for unusual brightness curves that turned out to be ordinary outgassing, trajectory predictions that were off by measurement error, nothing that warranted waking up humans in the middle of the night. But something about this alert made him pause. The confidence score 87%. In 3 years of testing, the AI had never assigned a confidence above 65% to any prediction. Jones opened the full report. What he read made him immediately forward it to 12 colleagues with a single-line message. Check K1 in 3 days. The machine thinks something's about to happen. The Comet Interceptor AI wasn't designed to predict the future, not exactly. It was trained to recognize patterns in 50 years of comet observation data like curves, spectroscopic signatures, orbital dynamics, outgassing rates, fragmentation events, everything astronomers had measured about comets since the 1970s. The training dataset included 247 well-documented comets, 89 confirmed fragmentation events, and over 4 million individual photometric measurements. Feed that much data into a neural network and it starts seeing correlations humans miss. Dr. Colin Snodgrass, who helped develop the AI system while working at ESA's Near-Earth Object Coordination Center, explained the logic in a January 3rd, 2026 paper. The algorithm doesn't understand physics. It doesn't know why comets fragment. What it does is pattern matching at enormous scale. It recognizes that comets which fragment tend to share subtle precursor signals, tiny asymmetries in brightness variation, specific ratios of gas species in their spectra, particular relationships between orbital distance and activity level. signals too faint or too complex for human analysis to catch reliably, but statistically significant across hundreds of examples. The AI flagged K1 based on 7 distinct anomaly indicators. First, the brightness curve showed a 3.2% asymmetry in how quickly it brightened versus how quickly it faded as it rotated. Most comets show symmetric curves. They brighten and dim at the same rate as different faces rotate toward the Sun. Asymmetry suggests structural differences, possibly cracks or voids that create irregular sublimation patterns. Second, the ratio of Cn to C2 emissions cyanogen to diatomic carbon measured 0.89. The normal range for long-period comets is 0.5 to 0.7. Ratios above 0.8 correlate with comets that fragment within weeks of perihelion. Third indicator K1's dust-to-gas ratio had increased by 18% between October 25th and November 5th. Gradual increases are normal as comets approach the Sun, but jumps above 15% often precede structural failures. The nucleus is shedding more dust relative to gas, suggesting surface layers are breaking down. Fourth, the sodium emissions. The AI had been trained on the 4 previous golden comets, and it recognized K1's emission profile matched the pattern seen days before Comet 333P/linear fragmented in 2010. Fifth, sixth, and seventh indicators were more technical microvariations in the orbital elements suggesting non-gravitational forces acting asymmetrically on the nucleus. A specific pattern in how the coma brightness varied with distance from the nucleus, and a subtle blue shift in the carbon monoxide emissions that indicated gas escaping preferentially from one hemisphere. Individually, any of these signals might mean nothing. Together, they formed what the AI called a pre-fragmentation syndrome, a constellation of symptoms that preceded 76% of observed comet breakups in the training data. Have you ever had a feeling something was wrong before you could articulate why? Maybe your car was making a sound that wasn't quite right. Or a friendship felt strained before any argument happened. That's pattern recognition operating below conscious awareness. Your brain detecting signals too subtle to name but too consistent to ignore. The Comet Interceptor AI was doing something similar, except it could name the patterns 87% probability fragmentation, confidence interval 48-96 hours. Jones and his colleagues watched K1 closely on November 10th. Nothing unusual. November 11th. Still intact. By November 12th morning, some were joking that the AI had embarrassed itself with a false alarm. Then Gianluca Massi's images came through that evening showing 7 fragments. The prediction window 72 hours. The actual fragmentation 68 hours after the alert. Error margin 5.6%. The AI had called it almost perfectly. I felt my skin prickled when I saw the fragmentation images, Jones admitted during a December 30th webinar. Not because K1 broke apart comets do that, but because a machine had seen it coming by recognizing patterns invisible to human experts. It's like watching a chess computer calculate 20 moves ahead. You know it's just processing data, but it feels almost clairvoyant. The story would have ended their impressive AI prediction. Useful for future comet monitoring except Dr. Michael Marset from the European Southern Observatory decided to feed 3 I/Atlas data into the same algorithm just to see what would happen. He didn't expect meaningful results. The AI was trained on solar system comets, and 3 I was an interstellar visitor with completely different characteristics. Besides, 3 I had already passed through its close approach and was heading outbound. Any prediction would be too late to matter. Marset ran the analysis on December 28th, using archival data from 3 I's July through September observations. The algorithm processed for 17 minutes, unusually long, suggesting it was having trouble fitting the data to its training patterns. Then it produced a result that made the Marset check his code for bugs. Anomaly detected object exhibits pre-fragmentation syndrome. Estimated fragmentation already occurred or imminent. Confidence 79%. Wait. 3 I hadn't fragmented. Astronomers had watched it continuously from July through October. No breakup. No fragments. It remained intact as it climbed outward past Jupiter's orbit. The AI was wrong this time. Except, and here's where things get genuinely unsettling, Mars-Set noticed a caveat in the AI's detailed report. Note object displays post-perihelion stability anomaly. Predicted fragmentation may have occurred prior to detection, or may manifest as delayed structural failure. I nearly dismissed it, Mars-Set wrote in a January 5th blog post. Until I check something. We assumed 3 I'd been discovered soon after entering the inner solar system. But objects on hyperbolic trajectories move fast, 3. I was travelling at over 33 kilometres per second relative to the Sun. I calculated how far it would have travelled in the 3 months before its July discovery. Turns out 3, I could have crossed Mars's orbit as early as March 2025, completely undetected because it was still faint and nobody was looking in that region of sky. If 3 I had entered the inner solar system in March, and if it had fragmented back then as the AI suggested, any fragments would have separated and evolved their own trajectories over the following months. By July, when 3 I was discovered, those fragments could be millions of kilometres away, too faint to detect in the glare of the brighter parent object. You'd only notice them if you went looking specifically. And why would you? Nobody knew 3 I had fragmented because nobody knew to look for the fragments. Except maybe one fragment wasn't too faint. Maybe one fragment followed a trajectory that kept it relatively close to Earth. Maybe that fragment got bright enough to be catalogued by a survey telescope in May. Maybe we called it C2025K1 and assumed it was a different object entirely until the chemistry revealed otherwise. Doctor. Althea Moorhead from NASA's Meteoroid Environment Office ran trajectory simulations on January 7th testing whether K1 could be a fragment of 3 I. She used the known orbits of both objects and calculated backward, allowing for uncertainties in position and velocity. There exists a solution space, her preliminary report stated, in which 3 I fragmented in early March 2025 near 1.8 AU from the Sun, producing multiple fragments including one that matches K1's observed orbit as of May discovery. The probability of this scenario given the observational constraints is approximately 23% low, but not negligible. 23% isn't proof, but it's not dismissal either. It's the mathematical equivalent of, this might actually be possible. And if it's true, if K1 really is a fragment of 3 I separated months before either was discovered, then the AI didn't just predict K1's fragmentation, it retrospectively diagnosed 3 I's breakup from subtle signals in data nobody had properly analysed. But here's what keeps Jones awake at night. The AI flagged 6 other objects in 2025. 6 comets or asteroids that triggered its anomaly detection protocol with confidence scores above 60%. None of them fragmented. None showed obvious unusual behaviour. The AI's report labelled them as long-term anomalies monitor for delayed manifestation, as if whatever pattern the algorithm detected might not appear immediately, as if these objects are ticking time bombs with unknown fuse lengths. The really disturbing implication, Jones said during that December webinar, is that the AI might be detecting a signal we don't understand yet. Maybe it's recognising objects that share the same origin as K1 and 3 I, other fragments from that hypothetical March breakup, or pieces of other parent bodies we haven't connected. The algorithm can't tell us what it's seeing, only that it sees something. It's like a dog that starts barking at an empty corner of the room. You don't see the threat, but the dog's senses are picking up something yours can't. Do you trust pattern recognition more than your own eyes? If a machine tells you something is wrong but you can't see the problem, do you believe the machine or your senses? These aren't academic questions anymore. We're entering an era where AI can detect astronomical anomalies before human observers notice them, where algorithms trained on past events can forecast future ones with uncomfortable accuracy, where the next surprise might not surprise machines at all, even as it blindsides us. The 6 flagged objects are being monitored closely. Maybe they'll remain quiet, proving the AI's false positive rate isn't perfect. Or maybe, one by one, they'll start showing the same symptoms. K1 displayed the golden glow, the organised fragmentation, the impossible chemistry. Maybe we're not dealing with 2 unusual objects, but with dozens, a whole population of interstellar or hybrid objects infiltrating our solar system. And the AI is the canary in the coal mine detecting the pattern while we're still arguing about whether 2 data points constitute a trend. Which brings us to the biggest question lurking beneath this entire investigation. If K1 and 3I are related, if they're fragments of something larger, if there are potentially dozens more objects with similar characteristics, and if they're arriving from or passing through the Hills-Cloud boundary where interstellar and solar system material mix, then we need to confront a possibility that challenges everything we thought we knew about our cosmic neighbourhood. What if our Oort cloud isn't purely ours? The Oort cloud is supposed to be ours. That's the foundational assumption of vast spherical shell of icy bodies surrounding our sun, remnants from the solar system's formation 4.6 billion years ago, gravitationally bound to our star, existing in frozen stasis at the edge of the sun's influence. Textbooks describe it as the solar system's attic, filled with primordial relics that occasionally get nudged inward to become the long-period comets we observe. It's our material, our history, our neighbourhood. Except what if it's not? What if the Oort cloud is less like a private backyard and more like a public park, a space we share with visitors, immigrants, and squatters from across the galaxy, Doctor? Suzanne Falzner from the Max Planck Institute for Radio Astronomy has spent the last decade studying something most astronomers prefer to ignore: stellar flybys. Our sun isn't alone in the galaxy. It's surrounded by billions of other stars, all orbiting the galactic centre in a complex gravitational dance. Occasionally, maybe every few 100,000 years, another star passes close enough to our solar system to gravitationally disturb the Oort cloud, shaking loose comets and potentially exchanging material. The traditional view treats the Oort cloud as static, Falzner explained in a January 8th interview with Sky and Telescope. But it's actually incredibly dynamic. Every stellar encounter stirs it. Some encounters strip away outer Oort cloud objects, sending them into interstellar space. Others deposit material from the passing star's own debris field into our cloud. Over 4.6 billion years and countless stellar encounters, the Oort cloud has become at least partially a dumping ground for interstellar junk. The math supports this uncomfortable conclusion. Falzner's simulations, published in Astrophysical Journal in 2019 and updated throughout 2024 to 2025, suggests that between 10% and 40% of objects currently in our Oort cloud might be captured interstellar material rather than native solar system debris. That's not a fringe hypothesis, that's a peer-reviewed estimate based on well-understood gravitational dynamics. 1 in 10 objects we call ours might have formed around other stars. The implications hit different when you apply them to K1. If K1 originated in the Hills cloud, that transitional zone where solar and galactic gravity compete, and if that region contains a substantial fraction of captured interstellar material, then K1 might technically be gravitationally bound to our sun while chemically belonging to another stellar system entirely. It's like finding out the family heirloom you inherited actually came from an estate sale 3 generations ago. It's in your house. You own it legally, but its origins are elsewhere. Dr. Simon Portuguese Zwart from Leiden University took this idea further in a provocative January 10th paper titled The Oort Cloud as Galactic Archaeological Record. He argues that captured interstellar objects don't just contaminate our cloud randomly, they carry signatures of their origin that can reveal information about nearby stellar environments millions of years ago. Every captured object is a time capsule, he wrote, preserving chemical and isotopic information about the star system where it formed. If we could systematically study captured objects in the Oort cloud, we'd essentially be doing galactic archaeology, reconstructing the history of our stellar neighbourhood by analysing samples it left behind. K, 1 and 3. I might be exactly those kinds of samples. Their chemistry, the unusual PaH ratios, the deuterium signatures, the sodium abundance could be telling us about a stellar system that existed within a few light years of our Sun sometime into the past million years. Maybe one of those stellar flyby candidates identified in the Gaia data. Maybe HD 7977 or Gliese 710 didn't just pass near our Sun. Maybe they shed debris that got captured, creating a population of chemically distinct objects that we're only now beginning to identify. But there's an even more radical possibility, one that Dr. Amaya Moreau-Martin from the Space Telescope Science Institute proposed during a virtual conference on January 12th. What if the contamination is ongoing? What if our solar system is constantly accreting interstellar material, and the rate has increased recently? We know interstellar space isn't empty, Moreau-Martin explained. There's dust, there's gas, and occasionally there are larger objects, rogue planets, ejected comets, debris from stellar collisions. Our Sun ploughs through this material as it orbits the galaxy. Most of it just passes by. But some gets gravitationally captured, especially in the Oort cloud where binding energies are extremely low. The question is, has the density of interstellar material in our local neighbourhood changed recently? Recent observations suggest it might have. The Sun is currently passing through what astronomers call the local interstellar cloud, a region of slightly higher gas and dust density within the larger local bubble, a low-density cavity carved by ancient supernovae. We entered this cloud approximately 100,000 years ago, and will remain in it for another 10,000 to 20,000 years. During this passage, the rate of interstellar material encountering our solar system increases. Not by huge amounts, we're talking maybe 20 to 30% higher than baseline, but enough that capture rates into the Oort cloud could rise measurably. If the capture rate increased 100,000 years ago, Moreau-Martin continued, and if the typical time for a captured object to get perturbed inward from the Oort cloud is tens of thousands of years, then we should be seeing an uptick in interstellar-looking objects arriving in the inner solar system right now. And we are. Oumuamua in 2017, Borisov in 2019, 3, Y in 2025, possibly K1 and potentially those 6 objects the AI flagged. That's 5 confirmed or suspected interstellar visitors in 8 years compared to 0 in all previous human history. Think about what that means for a second. Before 2017, we'd never definitively detected an interstellar object. Now we're averaging almost 1 per year. Either we got incredibly lucky with telescope improvements right when interstellar objects coincidentally started arriving more frequently, or the arrival rate genuinely is increasing because our solar system is moving through a richer region of the galaxy. The interstellar contamination theory, as it's becoming known in the literature, solves several puzzles simultaneously. It explains why K1 and 3I have identical chemistry despite supposedly different origins. They're both contamination from the same interstellar source, captured at different times. It explains the golden glow and unusual compositions they formed in stellar environments with different chemistry than our Sun's protoplanetary disk. It explains the organized fragmentation interstellar objects might have internal structures different from native solar system comets due to formation in different temperature and pressure regimes. And critically, it explains the timing. Why 2025? Why two related objects in the same year? Because we're not seeing coincidence, we're seeing statistics. If the Oort cloud contains thousands or tens of thousands of captured interstellar objects acquired over the past 100,000 years, and if those objects are now being perturbed inward at random intervals, then occasionally you'd expect clusters, years when multiple related objects arrive nearly simultaneously, just like buses that supposedly run every 10 minutes but then 3 show up at once. Doctor. Walter Harris from the University of Arizona ran Monte Carlo simulations modelling this scenario. Published January 14th, he assumed a population of 50,000 captured interstellar objects in the Oort cloud, about 2% of the estimated total Oort cloud population, and simulated perturbations over 1000-year periods. In approximately 8% of simulated millennia, his paper reported, 2 or more objects from the captured population entered the inner solar system within a single calendar year. In 1.2% of millennia, 3 or more arrived. The 2025 K1/3R pairing falls well within expected clustering statistics if the contamination hypothesis is correct. 1.2%. That's roughly once every 83,000 years. We happen to be alive during one of those millennia. Either we're extraordinarily lucky, or, and this is the uncomfortable alternative, 2025 isn't special. Maybe clustering happens all the time, and we only noticed because our telescopes finally got good enough to detect these objects. How many previous centuries saw multiple interstellar visitors arrive undetected? Because nobody was watching with sufficient capability. The philosophical question underneath all this is profoundly unsettling. If significant portions of our Oort cloud originated elsewhere, if the boundary between solar system and interstellar space is blurrier than we thought, then what does it mean to be from our solar system is Earth special because it formed from solar nebula material? Or is that an arbitrary distinction when our entire cosmic neighbourhood is constantly exchanging material? Here's an analogy that might help. Imagine your family has lived in the same house for 4 generations. You think of it as your ancestral home, filled with furniture and belongings that define your family history. Then you discover that 20% of the furniture actually came from neighbours' estate sales over the decades, mixed in so thoroughly you can't distinguish inherited pieces from acquired ones without chemical analysis. Does that change what home means? Does it matter that some of your heirlooms aren't technically ancestral? The Oort cloud is that house. K1 and 3I are the furniture we're just now analysing carefully enough to realise it didn't all come from the same source. And the discovery is forcing us to reconsider our cosmic identity. But if contamination is real, if our solar system has been accreting alien material for millions of years, then we need to address the elephant in the room, or rather, the fleet of elephants potentially drifting through the outer solar system right now, carrying the same chemical signatures, following the same pattern, waiting for their orbits to bring them close enough for detection. Because K1 and 3I might not be unique. They might be the first we've studied carefully, but statistical models suggest they're far from alone. The question is, how many more are coming, and how soon? They're already here. That's the conclusion emerging from survey data analysis conducted throughout late 2025 and early 2026. Not they might arrive someday, or we should watch for them. Present tense, already detected, already catalogued, already drifting through our solar system carrying the same chemical fingerprints as K1 and 3I. We just haven't connected the dots yet because until recently, nobody knew what pattern to look for. Dr. Kwanzi Ye from the University of Maryland runs the Comet Identification and Observation Project, essentially a database that tracks every catalogued comet and suspected comet observed since systematic surveys began. In January 2026, he published a paper that sent quiet shockwaves through the small world of comet specialists. The title was refreshingly direct. 8 additional objects display K1/3 I-type spectroscopic anomalies. 8, not 1 or 2 statistical outliers you could dismiss. 8 objects showing the same golden sodium emissions, the same unusual PAH ratios, the same isotopic signatures that flagged K1 and 3 and as special. I started with a simple question. Ye explained during a January 16th press briefing, if K1 and 3I represent a recognisable class of object, how many others in our catalogues belong to that class but went unrecognised because nobody was looking? He wrote software to scan spectroscopic databases archives from decades of observations by dozens of telescopes searching for specific markers. Sodium emission intensity above threshold, CnC2 ratios exceeding 0, 75 deuterium to hydrogen ratios between 150 180 ppm, elevated PAH concentrations. The algorithm flagged 23 candidates. Manual review narrowed it to 8 confirmed matches. The 8 aren't obscure objects lost in obscure data sets. Several are well-known comets that astronomers have observed for years without recognizing their unusual chemistry. See 2017 K2 Pan-STARRS. A long-period comet that passed through the inner solar system in 2022 showed sodium emissions at 78% of K1's intensity. See 2021 A1 Leonard. One of the brightest comets of 2021 displayed CnC2 ratios of 0.81 in archival spectra that nobody thought to question at the time. Even C2020 F3 Ni Eowise, the spectacular naked-eye comet that millions photographed during the summer of 2020, showed deuterium ratios of 165 ppm, remarkably similar to K1's 168 ppm. Think about that for a moment. Neowise. You might have seen it yourself if you were watching the sky. In July 2020, a bright streak visible just after sunset. Millions of people photographed it. Astronomers studied it extensively. And nobody realised they were looking at a potential interstellar contamination object until Ye's retrospective analysis 5 years later. How many other unusual objects have we watched, photographed, and catalogued without recognising their significance? The 8 confirmed objects span a range of orbital characteristics. 3 are long-period comets like K1 with Ophelia in the Oort cloud region. 2 are on hyperbolic trajectories like 3I and confirmed interstellar visitors. 3 occupy intermediate orbits, eccentricities just barely below 1.0, suggesting they're either native objects on the edge of being unbound or captured interstellar objects whose orbits have been modified by planetary encounters. The orbital diversity, Ye noted, supports the contamination hypothesis. We're seeing a mixed population, some native objects that formed in unusual environments, some captured interstellar visitors, some hybrids that have complex histories involving both solar system and interstellar phases. But 8 confirmed objects with 5 more years of searching just archival data means the real population is certainly larger. Doctor, Alan Fitzsimmons from Queen's University Belfast ran statistical extrapolation on Year's findings, published January 19th. If we detected 8 objects in existing archives which represent perhaps 5% of all comets ever observed spectroscopically, he calculated, and if detection efficiency for these anomalies is around 40% given typical observation quality, then the true population of K1/3 I-type objects passing through the inner solar system in recent decades likely numbers between 30 and 80. Most went undetected or were detected but not analysed sufficiently to recognise their unusual chemistry. 30 to 80 objects. That's not an occasional anomaly, that's a population or a phenomenon. A whole class of solar system inhabitants we're only now learning to identify. And those are just the ones that came close enough and bright enough to be catalogued. How many more remain in the outer solar system? Too distant and faint for detection. The Legacy Survey of Space and Time, LSST, operated by the Vera Rubin Observatory in Chile, promises to change our detection capabilities dramatically. Starting in late 2025, LSST began systematic surveys with unprecedented depth and coverage, imaging the entire visible sky every few nights. Dr. Matthew Holman from the Center for Astrophysics, Harvard, and Smithsonian ran simulations predicting LSST's detection rates for K1/3 I-type objects. His January 21st report estimated that LSST should detect between 15 and 40 such objects per year once fully operational. That's a factor of 10 increase over current detection rates, Holman explained. Within 5 years, we'll have hundreds of these objects in our catalogues. Within a decade, we'll understand their population statistics, orbital distribution, and potentially their origins well enough to test the contamination hypothesis rigorously. We're at the beginning of the discovery phase that will either revolutionize our understanding of the Oort cloud or prove that K1 and 3I were extraordinary outliers. But there's a subset of objects that worries researchers more than the confirmed distant comets. The near-Earth contamination candidates. Remember those 6 objects the Comet Interceptor AI flagged with high anomaly scores? 2 of them are near-Earth asteroids, objects whose orbits cross Earth's orbit, bringing them within a few million kilometres of our planet. Both are scheduled for close approaches in 2026 and 2027. 2024 PT5 is the first, discovered in August 2024 by the Atlas survey. It's a small asteroid, perhaps 10 metres across, on an orbit that brings it within 0.03 AU of Earth, about 4.5 million kilometres in September 2026. Initial spectroscopy showed nothing unusual, but the AI flagged it with a 68% anomaly score. Dr. Richard Binzel from MIT obtained follow-up spectra in December 2025 and found elevated sodium features and unusual silicate absorption bands. PT5's surface composition doesn't match typical near-Earth asteroids. His January 24th paper concluded, "It resembles material we'd expect in a comet nucleus more than a rocky asteroid. If PT5 is a dormant or extinct comet nucleus with K1/3 I-type chemistry, its September close approach offers an unprecedented opportunity for detailed study." The second flagged object is even more intriguing, 2023 FWW13. This one isn't just passing near Earth, it's a quasi-satellite. An asteroid that's been loosely orbiting Earth for several years, dancing in a complex gravitational resonance. Discovered in March 2023, FW13 is about 15 metres across and will remain in Earth's vicinity until at least 2028. The AI assigned it a 71% anomaly score. Spectroscopic follow-up in January 2026 revealed, you guessed it, sodium emissions and deuterium ratios consistent with K1/3 chemistry. Having a K1/3 I-type object in near-Earth space is scientifically invaluable. Dr. Amy Mainzer from the University of Arizona told reporters on January 26th, It's close enough for detailed radar observations, maybe even a spacecraft mission if we act quickly. We could potentially determine its rotation state, internal structure, precise composition, all the things we're guessing at with distant comets. FW13 might be the Rosetta Stone that unlocks this whole mystery. But proximity cuts both ways. FW13's orbit is unstable over long timescales. Eventually, maybe in decades, maybe centuries, its quasi-satellite dance with Earth will end. It might get ejected back into heliocentric orbit, or it might experience a closer gravitational interaction with Earth, a very close interaction. We're not talking about impact risk in the near term, Mainzer clarified. But over centuries there's a non-zero probability. Having objects of unknown composition and potentially unusual structural properties in near-Earth space introduces uncertainty into impact risk assessments. Here's a question that's been keeping planetary defense specialists awake if K1/3i type objects have different internal structures than typical solar system bodies, those onion layers. Those organized fragmentation patterns, do they also respond differently to deflection attempts? If we ever needed to redirect one away from Earth impact trajectory, would standard kinetic impactor or gravity tractor techniques work as predicted? Or would we be surprised by unexpected fragmentation or unusual response to applied forces? Nobody knows. We've never tested planetary defense systems on interstellar contaminated objects, because until 2025 we didn't know such things existed. The population estimates keep growing as more archival data gets analysed and new objects get discovered. By late January 2026, the confirmed and suspected count of K1/3i type objects reached 17, with another 30-something under investigation. The Catalina Sky Survey reported detecting 2 new objects in early February showing preliminary spectroscopic matches. LSST identified a faint comet at 12 AU, twice Jupiter's distance, with unusual emissions consistent with the pattern. We're watching a new category of object emerge in real time. Doctor, he reflected during a February 2nd webinar. It's like suddenly having glasses that let you see in infrared, and realising the room you thought was empty actually has dozens of occupants you couldn't see before. The objects were always there. We just developed the tools and knowledge to recognise them. But recognition is only the first step. Now comes the harder question: where exactly are these objects coming from? And what's the long-term significance of having our solar system contaminated, if that's the right word, by this much foreign material? Because if the population is as large as statistical models suggest, if we're detecting only the tip of a much larger iceberg, then the Oort cloud might not be a pristine record of our solar system's formation. It might be a cosmic landfill, collecting debris from across the galaxy, mixing it with native material until distinguishing origin becomes nearly impossible. And somewhere in that mixture, K1 and 3i and their siblings carry stories we're just beginning to learn how to read. February 8th, 2026. K1's fragments have spread across 180,000 kilometers of space, each piece still glowing that distinctive gold, fading slowly as they drift outward past Mars's orbit. 3i/Atlas is beyond Saturn now, racing toward the heliopause at 33 kilometers per second, carrying its secrets back into the darkness between stars. In 6 years it'll cross Pluto's orbit. In 20, it'll leave the solar system entirely, becoming once again what it was before July 2025, an anonymous wanderer in the galactic void, indistinguishable from billions of other icy bodies tumbling through interstellar space. But the story they started isn't ending. It's accelerating. LSST detected 3 more candidate objects in the first week of February alone. The European Space Agency's Euclid telescope, primarily designed to map dark matter, accidentally captured spectroscopic data on a faint Oort cloud object at 8000 AU showing sodium emissions consistent with the K1/3 orbital profile. NASA's James Webb Space Telescope, between exoplanet observations, was tasked with examining 2023 FW13 during its February 15th close approach 4.2 million kilometers from Earth, close enough for JWST's infrared instruments to detect thermal emissions and map surface composition in unprecedented detail. What we're witnessing, Dr. Michelle Bannister from the University of Canterbury said during a February 11th conference, is the birth of a new field of study, interstellar archaeology. We're learning to read the history written in contaminated objects, extracting information about stellar environments light years away and millions of years in the past. K1 and 3 are the first texts we've learned to translate, but they're part of a vast library we're only beginning to catalogue. The implications extend far beyond academic curiosity. If our Oort cloud contains thousands of captured interstellar objects, if they're continuously being perturbed inward, if their chemistry and structure differ from native solar system material, then our entire understanding of comet populations needs revision. The statistical models we use to estimate impact risks, the assumptions about volatile composition we apply to planetary formation theories, the baseline chemistry we assume for early solar system conditions, all of it might be contaminated by interstellar noise we didn't know to filter out. Dr. Paul Chodas, who manages NASA's Center for Near-Earth Object Studies, addressed this concern in a February 13th statement. The discovery of interstellar contaminated objects doesn't change our assessment of near-term impact risks. We track and characterize objects individually based on observed properties, not statistical assumptions. However, it does introduce uncertainty into long-term probabilistic models. If 10 to 20% of long-period comets originate from captured interstellar material with potentially different structural properties, we need to account for that diversity in our simulations. Translation. We're not in immediate danger, but we're less certain about the century-scale and millennium-scale impact probabilities than we thought we were 6 months ago. That's the price of learning something fundamental about your cosmic neighbourhood. You discover how much your previous confidence was built on incomplete information. But there's an optimistic angle here too, one that Dr. Sarah Seeger from MIT emphasized during a February 16th TED Talk that quickly went viral. Finding interstellar objects isn't just about identifying threats or correcting models, she argued. It's about access. Every captured object in our Oort cloud is a sample from another stellar system material we can potentially study up close, without travelling light years. It's like having geological samples from distant countries delivered to your doorstep. We're not just discovering that our solar system is contaminated, we're discovering that we have free samples from across the galaxy. The long-term vision is already taking shape. The Comet Interceptor mission, scheduled to launch in 2029, was originally designed to rendezvous with a pristine long-period comet. Now, mission planners are seriously discussing retargeting it toward one of the K1/3 I-type objects if a suitable candidate appears. We want the most scientifically valuable target, Dr. Grant Jones explained in a February 18th mission update. And valuable now means objects that can tell us about interstellar chemistry and formation conditions. A confirmed contamination object might be more valuable than a native comet. China's space agency announced on February 20th that they're considering a sample return mission to 2023 FW13, the quasi-satellite with K1/3 chemistry. The mission timeline suggests a launch in 2028, rendezvous in 2029, and return with samples by 2032. If successful, it would be the first time humans have held material confirmed to originate from beyond our solar system, not just studied from a distance with spectrographs, but actually touched, analysed in laboratories, subjected to every test we can devise. Think about what that means. Right now, everything we know about K1 and 3I's chemistry comes from remote observations light analysis, orbital mechanics, pattern matching in spectra, powerful techniques, but indirect. Having actual samples changes everything. We could determine precise isotope ratios, identify organic molecules too complex for spectrographic detection, measure physical properties like density and strength, maybe even find preserved traces of the radiation environment where these objects formed. It's the difference between looking at photographs of a country and actually visiting. Meanwhile, the AI continues flagging new candidates. As of February 22nd, the anomaly list includes 11 confirmed matches, 23 high-probability candidates, and 47 objects requiring follow-up observations. The pattern recognition that predicted K1's fragmentation is now being applied retrospectively to decades of comet data, and prospectively to new detections. Dr. Colin Snodgrass, who helped develop the algorithm, told journalists on February 24th. The AI is getting better at this. It's learning from each new confirmed case, refining its pattern recognition. Within a year, we might have automated systems that flag potential contamination objects within hours of discovery rather than weeks or months. Automated detection of interstellar visitors. That's the endpoint of this investigation, a future where unusual objects don't surprise us, because algorithms spot them immediately and we have protocols for rapid follow-up observation. A future where 2025's shocking discoveries become routine identifications, where golden comets and organised fragmentations are expected rather than anomalous, where we understand enough about the contamination population to predict their behaviour and origins. But we're not there yet. We're still in the discovery phase, still connecting dots, still surprised by each new piece of evidence, and there are pieces we haven't found yet. Guaranteed. Here's what keeps astronomers excited, and slightly nervous statistical models suggest we've detected maybe 5 to 10% of the K1/3I type objects currently in the inner solar system. The rest are either too faint at the wrong orbital positions for observation, or simply haven't been looked at with sufficient detail. Over the next 5 years, as LSST and other next-generation surveys come fully online, we'll find most of them. The population will grow from tens to hundreds, maybe thousands. Each new object will add data points, refine our understanding, possibly reveal new subcategories we haven't imagined yet. And somewhere out there, maybe 5,000 AU away, maybe 50,000 AU, deep in the Oort cloud darkness, there's another object beginning its inward journey. Could be a native comet, could be captured interstellar material, could be something in between. Its orbit is already determined by physics. It just hasn't happened yet from our reference frame. In 10 years or 50 or 200, it'll cross into the inner solar system. Maybe it'll display that golden glow. Maybe it'll fragment in organised patterns. Maybe it'll match K1/3I chemistry so precisely that we'll know without doubt it came from the same parent body. Or maybe it'll be completely different, a new type of contamination from a different stellar environment, with chemistry we've never seen before, challenging our models all over again. That's the nature of exploration. Each answer reveals 3 new questions. Each mystery solved uncovers deeper mysteries waiting beneath. Do you look up at the night sky differently now? Knowing that some of those faint points of light, the ones you can barely see, the ones you need binoculars or telescopes to detect, might be visitors from other star systems. Knowing that our cosmic neighbourhood is messier and more diverse than we thought, filled with immigrants and natives so thoroughly mixed we can barely tell them apart. K1's fragments will fade from visibility within months, becoming too faint for all but the largest telescopes to track. 3I will vanish into the darkness, its story unfinished, its origins still debated. but their legacy continues in the questions they forced us to ask, in the techniques we developed to study them, in the population of similar objects we're now learning to recognise. The twins taught us that coincidence has limits, that chemistry doesn't lie, that the universe is more interconnected than we assumed, with material flowing between star systems, contaminating and enriching each other's planetary environments, that our solar system isn't an isolated island but a shoreline where interstellar tides deposit debris from across the galaxy. The next visitor is already on its way. The AI might flag it, the surveys might detect it, the spectrographs might reveal its golden signature, and when it arrives, we'll be ready, not surprised, not confused, but prepared with questions refined by everything K1 and 3I taught us. Because the most important discovery of 2025 wasn't two unusual objects. It was learning to see what was always there, hidden in plain sight, waiting for us to develop eyes capable of recognising it. And now that we can see, now that we know the pattern, the universe looks different, fuller, stranger, more wonderful than we dared imagine. Keep watching, keep questioning. The sky still has secrets to share, and we're just learning the language it speaks.